Good afternoon, everybody. Thank you for coming to my session. Next 50 minutes or so, I will talk about the stuff we are exploring with my colleagues in Deltatre Innovation Lab. We've been playing around in the last few months on AI-based methods to try to enhance and implement a video restoration pipeline. In a moment, we'll see three basic building blocks that combined together will enable us to automatically perform video restoration. Before to start, I have a question for you. How many of you are deep learning practitioner or deep learning engineers? By raise your hands, please. OK. I won't go deep on fundamentals and on code in this session, given the time we have. But feel free to ask me anything later. I will reserve some time for questions, or ask me later after the session as well. First, what is video restoration? It's if you're not familiar with the media stuff, it's a combination of techniques that enable us to, for instance, increase resolution of videos, increase frame rate, remove glitches, errors, damages, deblurring, add objects, remove objects, watermarks, and why not? We can also colorize video, meaning that from black and white, we can obtain colorized videos. The idea is our ideal target is to have a high definition image. But we can start to obtain this, for example, from low resolution images or images with artifacts, maybe due to compressions or damages depending on the source kind of video. The video can be blurred, can be time damages depending on the source of the video, for instance. There can be noise, as you can see. And combined all together, we may have an old video that we want to restore. There are many techniques that we can apply to obtain this. Mainly, some of them are manually, some of them are based on computer vision algorithms, others are statistics based. Now we see three methods that are quite brand new, based on AI. First, super resolution. Super resolution is a process that everybody knows thanks to CSI, meaning that we have a low-level quality, a low-level resolution image, and we can increase it, seeing details that otherwise would be impossible to see. This is not science fiction. It currently is possible to obtain something interesting, and now we see how. In the last few months, we started from an open source project and a paper that enable us to apply these techniques not only on images, but also on video, to obtain super video resolution. In this paper, you'll find all the details, and this paper also provides an implementation, open source implementation in PyTorch. These are all the details if you want to explore them. It is an evolution of an existing method done by the same people, which was applied to images. It was called Deep Back Projection Network. They extended it also to work for video. Make it simple, how does it work? It takes an input frame and a number of neighbor frames near it. We can define n almost as we like. Altogether, it extracts features and perform optical flow calculations, and combine all together. Combining all together and pass it to a recurrent neural network, where for each of these components and calculations, apply the single super image resolution, plus some improvements that enable us to obtain, from a low-level input, a super high-quality resolution, which has information not only from the starting input single frame, also from the neighbor ones, and this enables us to overcome issues like fast movements, blurring, and pixel obfuscation. So for each single frame, we'll take n neighbor frames and obtain a super resolution one. Of course, you can think that this is a quite heavy process, and it is. We didn't, currently, starting from the open source implementation, is not optimized at all. And given a very low resolution video, which we'll see later in the demo, it's a 30 frames per second at less than standard definition video. We obtain a super full resolution, meaning 2 key by 100 key, in about 2 hours. So, not optimized at all, but you obtain a very high quality resolution video. We'll see later in the demo, just in a moment. Let's pass to the other building block, video interpolation, meaning if we take 2 consecutive frames, we're able to invent and recreate new frames in between. This lets us to obtain 2 stuff. One, we can create slow motion videos starting from standard frame rates, meaning that we don't need high quality and high speed cameras to obtain similar slow down videos. On the other side, we can see these techniques as a way to increase the frame rate of existing footage. Maybe this is a very low frame rate, and increase it up to 30 frames, 60 frames, 90 frames per second as we need. How does it work? We started from an interesting research paper by NVIDIA Research, dated last year, which is called super slow motion. The idea is that we take 2 consecutive frames, we can decide to interpolate them almost as much as we want in between. So we can start from duplicating them, triplicating them, or as much as we want to slow down a video or increase its frame rate. The official implementation is not open source, but is available in the NGX framework, which is a new SDK from NVIDIA that let us, using the new RTX graphics card, to implement these kind of solutions, as well as super image resolution, super video resolution, and other AI-related interesting projects. Given our requirements to also be able to perform other stuff like we've seen before on video, we started from an open source implementation in PyTorch, which is available at this GitHub website. How does it work? So we take 2 input frames and pass them to an additional convolutional neural network that performs video flow, optical flow computation. And once we have this optical flow bidirectional from frame 1 to frame 0 and from frame 0 to frame 1, for each time step we want to interpolate, for each intermediate frame we want to create, we calculate an approximated optical flow at each time span between the original frame and the frame we are interpolating, and then create a mix of the 2 images thanks to a few computer vision algorithms that is warped, meaning that we can understand if an image if a pixel has been covered or not in the linear ones, and obtain very high quality interpolated features. Combining all together, for each time step, we are able to generate a new video. The flow interpolation convolutional neural network is based on the UNet architecture, which is able to pre-calculate and calculate all the optical flow using also high resolution features. Also in this case, given the open source implementation is not optimized, it is better than super resolution. As you can see, for triplicating the frame rate, it requires almost 11 minutes for the 7 seconds video at that resolution. Of course, this depends on the resolution of the source video you want to interpolate. And let's pass to the last building block, colorization. Meaning that there are new deep learning-based techniques that enable us to colorize image, meaning that from black and white grayscale pictures, we obtain realistic, plausible, colored pictures. And this applies also to video, too. We started from a state-of-the-art model from these projects, the Oldify by Jason Antic, which is a very smart guy that, leveraging the fast AI library, was able to obtain a very optimized model that performs quite well also on consumer hardware, as we see in a moment. But how does it work, simply? Simply put, at the core there is, again, a general adversarial network, which, given a grayscale image or a damaged image as input, is able to generate a restored image. Let's imagine this as apply style transfer, but maintaining the content and add a new style, which is color, to the image. So black and white images can become colored, but this component, this generator network, is able also to, as the training process goes on, to deblur and denoise images, all built in. The generator network is something derived from a dynamic unit architecture, similar to the one I've shown you before, which you can find implemented in FastAI library too. The interesting idea behind also the training sets that you can use. Usually, training GANs requires a lot of source data, but thanks to the idea that we want high-resolution images as target, as final output, if we have a lot of images, high-resolution images, colored one, we can apply transformation to them, make them grayscale, damage color, add in noise, add in artifacts, stuff like that, and use the original one as our target. So we have immediately thousands, if not millions of images that we can crapify, add noise, rumors, damage, and the targets, all in a supervised manner. In addition to this, we have to apply some changes to traditional architecture and to the unit I mentioned before. If we want to use these techniques on videos, we have to be sure that for each frame, we detect correctly the objects, the persons, the backgrounds, the foregrounds, in a reliable manner. To do this, we use feature networks derived as a ResNet, which is a very big ResNet that is able to, being trained on this image augmentation and crapified images, is able to detect all the issues in a consistent way. In addition to that, it has been introduced the self-attention method, meaning that using traditional approaches, we may obtain a problem like this, where similar components here, like the grass, is colored differently, even though it should be the same object. By using self-attention, we're able to colorize everything uniformly. So grass is grass, everywhere there is grass in the image, just to give an idea. And this enables also us to apply to video without using temporal modeling. So a video is a sequence of frames. We apply colorization frame by frame with no correlation between frames in the process. So this is also quite fast to perform. Last but not least, we need to measure the difference between the target images and the generated one, such a way the network can be trained and understand its errors to improve. We use a loss. This is a feature. It's a perceptual loss, which is able to give a number of the score which can measure the differences between the high-level features, meaning if something was to be colored in a specific color, is able to understand that if it uses another color, it's wrong. Or if in a hand is a hand and it's colored differently than a human hand, but maybe it becomes an alien hand, it understands that and it trains the generator network to improve. This feature loss used in this project is itself a deeper neural network, which is based on VGG16. Interesting, we said it is again is difficult to train. Jason Antic, thanks to folks from FastAI, Jeremy Howard and Sylvan Guger, were able to invent a new way to train GANs, meaning that they call no GAN because the training is performed in 3 steps. 2 of them are just traditional neural networks trained as traditional neural networks. And then just at the end of the process, they perform the GAN training as usual. This enables a lot of time saving, meaning that the state of the art can be obtained in less than an hour and a half using one GPU, a consumer GPU. Also, it is able to use the technique of pre-training networks and fine-tuning on GANs. This was very interesting from when they discovered in the projects, because it also can generalize to other tasks, meaning we have seen the colorized version, but we take the same network, we can apply and fine-tune them, meaning given a different starting training set, we can train the network a little bit to denoise it, to remove watermarks, to remove blurring, and stuff like that. As mentioning, the performance were very good using, thanks to fast AI and the optimized version of all the algorithms internally. So to obtain the 17 seconds video at this resolution, it just takes 4 minutes. Now, we have seen the 3 building blocks. What we did, in Deltatre Innovation Lab, we started to work on an enhancement pipeline, which combines all the 3 steps together. And given an old video archive, an old video or photo, it passes through these 3 steps, and we obtain a restored video. Let's see the results. Let's watch it together. So this is a low quality video where we apply the super resolution one. As you can see, details here are quite interesting. Then we apply colorization on the super resolution video. So color and quality is the same. And then on the right side, you see the ground truth video. It was a standard 720p video at 30 frames per second, which we upscaled to 60 frames per second, which is the last version there. Amazing. When we produced it, it was very incredible. But all this stuff is interesting, but we have few problems to consider. Generative AI is amazing technology, but we have to use it carefully. Meaning that if we create new images that doesn't exist, we can enter in problems on privacy, of the trueness of data, or factual historical fidelity. For instance, imagine that we can able to insert new frames, and in these new frames, we slightly modify a face, slightly modify details that, processed by other AI algorithms, can detect something that there wasn't there. Or we can replace features in image, and object tracking can understand that it's something that there was not there. So this poses new kind of problems that we must consider. And to limit these problems, we have to build better datasets, better source datasets. And regarding to datasets, there is also another problem. If you want to restore or invent something that our pipeline is able to manage, this stuff must be inside the training data. So apart from having a lot of data for instance, for colorization, which we take high-resolution images, crapify them, we have a lot of them. If you want to invent something that is not there, you have to be sure that it is in your data set. That's a key point. And it's something that we are working on, optimizing all these algorithms in the full restoration pipeline. That's all from my side. Thank you very much for your attention. Thank you. If you have any questions, or we can take it off later. Object recognition is inside the video implicitly, meaning that when you want to, for instance, the colorization part, object recognition is implicitly there thanks to the feature maps that the ResNet network is able to detect. The question is, do we perform object recognition in video? Yes, is it possible? Not with this pipeline, but if you can plug new components in this pipeline that can then do that with other models. Other models, for instance, they can recover the bounding box of the objects, bounding box of a person, of understand which kind of objects are there, but are different models that I not presented now. Two stuff here. In the slides, I put some reference. Don't forget to evaluate the sessions. It's very helpful to know and to improve for future sessions. And also, don't forget there is the startup for Microsoft initiative. There are a few startups from Microsoft, and they are happy to show what they are doing. So please, step by there and have a discussion with these amazing guys. Thank you very much again. See you next time. I'll have another session on Thursday afternoon, which we talk about action recognition in sports video using an AI-based method. Thank you again. See you. Enjoy the conference.